In this lesson, we will discuss testing the difference between two variances or standard deviations from two different samples. To do so, before we can begin, we need a new type of distribution called the F distribution. The F distribution shares some similarities to the chi-squared distribution in much the same way that the T distribution shares some similarities to the normal distribution. However, they definitely have different characteristics. First, as with all probability distributions, the total area under the curve is equal to 1. However, like a chi-squared distribution, this is a positive distribution that is skewed to the right. So we will never have negative test statistics or negative critical values. They will all always be positive. The chi-squared distribution is determined by a single degrees of freedom because it is used for a single sample. The F distribution is different because it is used for when we do have two samples. And as such, it actually relies on 2 degrees of freedom. The test statistic for an F distribution is actually quite friendly and much simpler than any other test statistic that we have had for any other hypothesis test. It is simply the variance of one sample over the variance of the other sample. Very simple, very easy to determine the test statistic. Each sample then is going to provide its own degrees of freedom. Because this is set up like a fraction, we refer to these as the degrees of freedom of the numerator and the degrees of freedom of the denominator. These degrees of freedom are, quite simply, 1 less than each of the appropriate sample sizes. The 2 degrees of freedom are going to affect the shape of the curve by pushing in different directions. The degrees of freedom of the numerator, as it gets higher, tends to push this side of the curve inward, kind of indenting it. Whereas the degrees of freedom of the denominator tends to push this side inward, the bigger it gets. So they both play a role in determining the shape of the curve, and they each kind of push inward in different ways, thus skewing it more to one side or the other if 1 degrees of freedom is significantly larger than the other. And if they are balanced, actually shaping this somewhat closer to a normal curve. Now, the mean of an F distribution is always equal to 1. When we combine that with another rule, the rule is that when we look at these two samples and their standard deviations, does it matter which one is used in the top of the fraction and which one is used in the bottom? Yes, it does. The larger standard deviation or variance is used for the numerator. This has a couple of effects. One, it guarantees that the test statistic is always larger than 1. If the top of the fraction is larger than the bottom, then the value of the fraction will be larger than 1. What this does then is, because the mean of the distribution is equal to 1, since the mean of the differences since the mean of the variances in ratio is always equal to 1 here, that means that all F tests will be right-tail tests. Or in the case of a two-tail test, it is only the right side that matters. So they are either going to be a right tail test, never a left tail, or a two-tail test where only the right side is relevant. Now, like the other distributions, we can either do a critical value or we can do a p-value. Like the chi-squared distribution and the t-distribution, since the shape of this distribution changes depending on the degrees of freedom, it is limited the same way that the t-table and the chi-squared table are, in that if the degrees of freedom is not shown in the table, then we would not be able to find the critical value. However, in this case, it's actually a little bit worse because it depends on 2 degrees of freedom. If either one of them is not visible in the table, then we would not be able to find the critical value. So just like the chi-squared distribution, we tend to use the p-value more often here. And for consistency in the real world of statistics, the p-value is certainly more often used than the critical value. So we therefore need a way to calculate probabilities under the curve. On the calculator, in the same distributions menu that we would find the t-CDF, the normal CDF, and the chi-squared CDF, there is also an f-CDF command, which has 4 parameters: a lower bound, an upper bound, just as we see for the normal or the t-distribution or the chi-square distribution. But we also need to give it the degrees of freedom for the numerator and the degrees of freedom for the denominator. Now, this being always a right tail test, it should be noted here that the upper bound will always be the calculator's version of infinity, because we will always, in these tests, be finding area to the right, either a right tail test or a two-tail test where the right side is the relevant side. Let's consider an example. A restaurant manager is designing a system that is intended to decrease the variance of the time that customers wait before their meal is served. Under the old system, a random sample of 10 customers had a variance of 400. Under the new system, a random sample of 21 customers had a variance of 256. At the 0.10 significance level, is there enough evidence to convince the manager to switch to the new system? So what we have here is the old system, which has a sample size of 10 and a variance of 400. We have the new system, which has a sample size of 21 and a variance of 256. Now again, which one of these we choose to as sample number 1 and which one is sample number 2 is going to be determined by which one has the larger variance or larger standard deviation. Since the 400 is larger than the 256, we're going to use the old system as sample number 1 and the new system, therefore, as sample number 2. This will then allow us to properly write our hypotheses. Now, our hypotheses are going to be very much like they have been for comparing two variances or two proportions or two means. Our hypotheses are going to be a statement that includes a statement of equality between the two, and a statement that they are not equal that will also indicate which test we have here. The idea here is that we would like to say that the new system works better. So what we're going to do is say that the original variation is bigger than the new system's variance. This also coincides with the fact that we are doing a right tail test. We also need the degrees of freedom for each sample. So we have our test statistic, which is going to come from the variance of our old system over the variance of our new system. Which, as usual, will give us a decimal value that is not the best to use, but we will use our calculator to not have to round it. In this case, we fortunately have a number of decimal places that is manageable, so we can just type that in directly. We also need the degrees of freedom of the top and bottom. The degrees of freedom of the numerator is 1 less than the sample size that variance came from. So in this case, the degrees of freedom of the numerator is 9. The degrees of freedom of the denominator is 1 less than its sample size. So 21 minus 1 is 20. Now in most F tables, these two degrees of freedom are values that we would certainly see in them. So we could go with a critical value method, a rejection region if we chose. But for the sake of consistency, we're going to go with the p-value method once again. So this being a right tail test, our p-value is going to be the probability of having a variance, of having an F value larger than our test statistic. And this is going to come from the FCDF from 1.5625 to the excessively large number that the calculator uses for infinity, with the degrees of freedom of the numerator being 9 and the degrees of freedom of the denominator being 20. This gives us a p-value of 0.1939. This p-value is certainly larger than the value of alpha that we were given, 0.10. And therefore, we would have the conclusion to fail to reject the null hypothesis. What this tells us then is that, yes, we can see in the numbers that from the samples, this new system, its sample did have a smaller variance. However, it also takes into account the size of the samples via the degrees of freedom. And the fact of the matter is that a sample of only 10 customers from the old system is very, very small. Both of these samples are relatively small, but the 10 in particular is quite small. So what we see here is that there isn't enough evidence to suggest that the population variances are different. We would need more data, perhaps a larger sample size. So we would say here there is not enough evidence to support the claim that the new system is better. Now, perhaps if we had done this with a larger sample size for the old system, it's possible that we would have found a different result. In fact, if you wanted to play around with that, we could simply put in suppose that we had a larger sample that came out with the same size variance. At a sample size of 20 for the old system, which would mean a degrees of freedom of 19, the p-value does drop to 0.1649, which is not that much smaller and still not enough to reject the null hypothesis, but we can see there that by having a larger sample there, it does reduce the size of the p-value. Now, this was a right tail test. Let's look at one more example with a two-tail test. In this case, you are deciding between two different stocks to buy. A stock's risk can be associated with the standard deviation of its closing prices. So if we look at its closing prices and see that sometimes it goes high, sometimes it goes low, it varies. And the more it varies, the more risk there can be. So you randomly select a sample of 30 closing prices of the first stock and 31 closing prices of the second stock, and find that they have standard deviations of 3.5 and 5.7 respectively. So we can call them stock A and stock B. For stock A, there is a sample size of 30, and the standard deviation, not the variance, the standard deviation here was 3.5. For stock B, there were 31 closing prices, and that had a standard deviation of 5.7. Once again, we need to figure out which of these two is bigger so that we know which one we're treating as the numerator and which is the denominator in our test statistic, which will then also affect the degrees of freedom of the numerator and degrees of freedom of the denominator. So in this case, it is stock B that has the larger standard deviation and therefore the larger variance as well. So we will treat stock B as our first sample and stock A as our second sample. This will again allow us to write our hypotheses. Now again, the null hypothesis is always going to be a statement of equality. So we will simply write sigma sub 1 squared is equal to sigma sub 2 squared. The alternative hypothesis then is either going to be not equals or greater than, because again, we will only ever have a right tail test or a two-tail test, where only the right side is relevant. In this case, it's not a matter of picking one of them to have a reduced variance or a reduced standard deviation. We're simply comparing the two to see which one has lower than the other. So we don't want a statement that's going to say this one is lower or that one is lower. We simply want one that says that they are not the same. And that's going to give us a two-tail test. Our test statistic then is going to be S sub 1 squared over S sub 2 squared. Now we saw this when we did hypothesis tests for a single variance or single standard deviation, that we can be given either of those two values because they are so closely related. The distribution and the test statistic are both based on the variance. So what we have to do here, unlike the previous example, here we have to take these standard deviations that we were given and actually square them. So if we are given the standard deviations, we need to square them to get the variances. But we don't have to do that until we actually reach the calculation of the test statistic. And this gives us 2.6522, etc. We also need to establish the degrees of freedom of the top and bottom. So our degrees of freedom of the numerator is going to be n sub 1 minus 1, where n sub 1 is 31, and therefore the degrees of freedom of the numerator is 30. The degrees of freedom of the denominator is n sub 2 minus 1, 30 minus 1, which gives us 29 for the degrees of freedom of the denominator. Our p-value then, and this being a two-tail test, our p-value is going to be 2 times the probability of getting a more extreme result, something further to the right than our test statistic. So we need our FCDF from our test statistic, 2.652, etc., up to the calculator's very large number, comma, our degrees of freedom of the top and degrees of freedom of the bottom. And in this case, we get a grand total of 0.0102, etc. And this is definitely less than our alpha value of 0.05. In this case, we would reject the null hypothesis. Now, the null hypothesis said that their variances were equal. So if we reject the null hypothesis, we are in turn accepting the idea that they do not have the same variance, that they have indeed different variances and therefore different risk. So there is enough evidence to suggest that their risk is not the same. Now, that being said, our interpretation of standard deviation is that it is average distance from the mean. What that means is that a larger standard deviation varies more, has more possibility of having different values and higher values and lower values, whereas a smaller standard deviation means that the values are more predictable. They can vary, but not by as much as the other. Therefore, we can conclude here that since stock A has the smaller standard deviation, it has the lower risk. Now, what you do with that would be up to you and your preferences as an investor and your goals as to whether you want the riskier stock or not. But this would allow us to see that the risk of stock B is higher than the risk of stock A. So once again, we see that the procedure for hypothesis testing is the same. We have claims, we have sample data, we have a test statistic, and we have a p-value or critical value that we compare either the test statistic or its p-value with either the critical value or alpha, respectively. And then we make our decision and conclude how we're going to go with this. The difference being here that before we write our hypotheses, we need to first figure out which of these is going to be treated as the larger, as the first sample, and which is going to be treated as the second, based on the idea that the test statistic is always calculated so that the larger variance or larger standard deviation is in the top. And that, in turn, guarantees that we are always looking at the right side. Our p-value will always be calculated from the right side of the distribution. Or if you use the F table and find the critical value, it will always be the right side critical.